Okay, so this presentation is meant to be a supplement material for the previous video, Introduction to Supervised Machine Learning Theory Part 1. In this video, I would like to share my perspective on the design of the growth function in the VC dimension. Now, I would like to point out that this might not be the typical way of introducing this topic for some people. I'm just trying to share my way of thinking when I learn about this idea. So the main objective here is to define a capacity or a complexity measure of a function set. This is a very big task, and as many mathematicians would say, is that if a problem is too complicated, let's try to simplify it first. So we'll first start with a simple version of the problem, maybe binary classification. We'll then state what we want mathematically, work with a smaller subset of the data, probably select a simple function set, say linear classifiers, then we'll enter the idea of growth function and the VC dimension. So a small note here, set theory is quite important in the sense that we will use a lot of sets in this presentation. So being familiar with the idea of sets is quite important. Here are some of the keywords we will be using along with the corresponding notation. So how do we define a capacity or a complexity measure? So if we continue our example from last time, that is a binary classification problem for weather forecasting. We have a sample space X with probability measure Px, and another sample space Y with probability measure Py. Now we want to map elements from X to Y using functions from this set of functions, calligraphic F, which could correspond to neural networks. And just a brief recap from last time, the main problem of machine learning is to minimize this objective function in problem 1, but to search through all measurable functions, which is impractical. Therefore, we settle with a particular function set of our choice, which then leads us to problem 2. And then by using the empirical mean, we arrive at problem 3. We did say that the ERM, empirical risk minimization, does minimize the true risk with high probability, provided that the VC dimension of the function set is finite. And at that time, we said that the VC dimension can be viewed as a measure of complexity for the function set. And this is a more formal way of explaining the PAC framework, which I explained in the previous video. Now in this talk, we will be more explicit on what we mean by complexity. And in this talk, I will use the term potentially expressive a lot, and I will use different fonts to distinguish different notions of the term expressive. And again, a little disclaimer here is that I don't think most people use these terminologies in this way, but this is just my way of viewing things here. So what do we want here? Ultimately, we want a number that tells us how potentially expressive f is on X. But the set X is just too big and too complicated. So let's first simplify the problem. Let's see if we can find a number that tells us how potentially expressive f is on subsets of X. Each subset has d samples. But this is still too complicated in the sense that there are way too many subsets you can actually choose. Too many subsets. So let's just simplify it further. Let's find a number that tells us how expressive f is on a particular set of samples from X. We'll start from here. So let's first work with a smaller subset of the data. So let's just choose d samples from X. I don't care what you pick. Let's just first pick d samples for now. So here are the d samples, and these are the y's, and this is the function set calligraphic f. So for starters, let's start with linear classifiers or linear indicator functions. Typically, some people might call this a set of perceptrons, where w is the weight vector and 1 here is the indicator function. So we have our set of perceptrons here, and we have a set of D samples from X. And let's consider the following question. How many distinct outcomes can I expect from F if I have this set of X's? So let me be a little bit more specific on what I mean by outcome here. This would be slightly easier if we start off with a simple example. Suppose we have three data vectors, x1 to x3, and two perceptrons, f1, f2. For each function, we'll send in the x's and store the outputs in a vector. So the inputs and the outputs in a vector. So each distinct vector is considered an outcome in this context. In this case, if these two vectors are different, then the number of distinct outcomes I can expect from F for this set X is 2. So this is where we define a new set. We use this notation. I first saw this kind of notation from the Simons Institute video. So F is the set of perceptrons. X, these X's from I equals 1 to D is the set of D samples from X. The question was, how many distinct outcomes can I expect from F if I'm given this particular set of X's? Well, we'll just list them out in this set. This is the set of distinct D-dimensional vectors. So if any two vectors are the same, we'll just pick one. We don't double count. With that, we can now have a notion of how expressive F is on a particular set of D samples from X. For starters, we could first use the cardinality of this particular set as a measure of how expressive F is on this particular set. And with that, we pretty much answered the easiest question within these three questions. So what quantity could tell us how expressive F is on a particular set of samples? Well, the cardinality of this set right here is a pretty good indicator. Now let's try answering the next question based on what we currently have. Now we want to ask how potentially expressive F is on subsets of X, with each subset having only D samples. So clearly, if I choose a different data subset, maybe it's this other set, which is also a subset of X, the cardinality of this set could also be different. And we need to remember that if the question is how potentially expressive F is on X, then we can choose any subset of size D from X. And this leads us to the idea of the growth function. Essentially, if we are to discuss how potentially expressive a function set F is on all subsets of D samples in X, we can find the maximum cardinality of this set, where the set of D samples is still from X. So potentially pretty much means maximum size in this context. So potentially means maximum, and the number of distinct outcomes represents the idea of expressive. So this definition of the growth function pretty much answers this question here. Now let's move on to the hardest question, and that is a number that tells us how potentially expressive F is on the entire set X. Now we need to introduce a new terminology called shattering. If the cardinality of this set is equal to 2 to the D, which means that all possible outputs can be obtained, then we say that F shatters this set of dx's. 2 to the D is the maximum number of possible outcomes here, since we are doing binary classification and the subset is of size D. With that, we finally arrive at the VC dimension. If the growth function tells us how potentially expressive F is on a set of D samples from X, then the subset with the maximum size, which the function set can shatter, can serve as a measure of how potentially expressive F is on X. In other words, we can also regard the growth function with respect to a function set being 2 to the d as a demonstration of the expressiveness of the function set. And how far can we push this d such that the function set is still capable of shattering the set is what we are asking. So this is the definition of the VC dimension, named after Professors Vladimir Vapnik and Alexei Chernenkus. It is essentially the largest possible d such that f can potentially shatter a set of d samples from X. So there you have it. We have briefly explained the notion of complexity of a function set by asking these questions and solving them one by one. So complexity refers to what I call potentially expressive here. So next time when we see someone discuss or refer to the VC dimension, I hope this video provides a useful perspective. Now, clearly there are more ways to define how expressive a function set is, and as this title suggests, the VC dimension is a relatively old measure. A relatively more recent measure is called the Rademacher complexity, proposed by Professors Peter Bartlett and Shahar Mendelsohn in 2002. And at first glance, it's quite complicated, but if you follow the thought process of how we got to the design of the VC dimension, this is actually going to look quite natural if we follow the steps of how I think when I explain the VC dimension. So I will leave this explanation for another time, maybe in the part 2 of the series on Introduction to Machine Learning Theory. And here are some of the other talks that I plan to record, so stay tuned. Here are some of the references. If I missed any, I would add the links in the description later. And I think that will be it for this video. Thank you very much.